So in this session, I will discuss the nonlinear modeling of reinforced concrete beams and columns. And before actually going to have a direct introduction of different nonlinear components which we can have in reinforced concrete beams and columns, I would like to give an overview of different nonlinear modeling approaches which are currently being used to capture the inelastic response of building structures. So we know that the first or most detailed approach is the micro modeling approach. A micro modeling approach means that you can model each component of your structure with many small three-dimensional finite elements, and then try to capture the inelastic action in a more fundamental manner. uh, so you will try to simulate the actual physics of your structure or structural component in this approach. So this is the most accurate approach, but again, at the same time, it is also the most time consuming approach. So if you have, for example, a reinforced concrete column or a reinforced concrete shear wall, so in that approach you will divide or discretize that into thousands of small elements, three-dimensional elements, and then you will try to capture that inelastic action or behavior at the most fundamental level or most micro level, you can say. So the second approach is actually the macro modeling approach. In that approach you actually focus more on the overall behavior or action versus deformation behavior of the reinforced concrete cross section and member. So this is macro modeling approach, in which you, instead of discretizing your element into thousands of small sub elements, you actually try to capture the behavior at the full cross section or full member level. So macro modeling approach, we focus on either uh, cross section, material, or member level. So material, cross section of the structure, and then also maybe at the member level. Different approaches are there in the macro modeling approaches. So two of the famous nonlinear modeling approaches in that are actually uh, distributed plasticity approach, in which you assume that the inelastic action uh, is, uh, uh, is distributed along some part of the length or full length of the element. So distributed plasticity. For example, a very famous approach is called fiber modeling approach, that in which you actually use the inelastic material or nonlinear material along the length of a particular element, or maybe full length also. So you distribute that action along the length of the member. The second approach in that is called concentrated plasticity approach or lumped plasticity approach. Concentrated or lumped plasticity approach, and the idea is that you can just concentrate the inelastic action at certain points along the length of the element, and in between those points you can use the elastic frame element, for example for beams and for columns. So in this approach, this is also sometimes called as the plastic hinge approach. There are different terminologies in different references available. So in this particular demonstration for modeling of reinforced concrete columns and beams, I will be focusing on this plastic hinge approach. So please keep that overall picture in mind, that what are the different other approaches available, and we are using just one of them. There can be several other methods to incorporate nonlinearity in your structural model also. So for this demonstration, I'll be focusing on the use of concentrated plasticity approach or plastic hinges uh, for modeling the reinforced concrete beams and columns. So I'll start with what a plastic hinge is. So you can see here that, for example, if we have uh, a reinforced concrete column here, and This column is subjected to, let's say, bending moment, some bending moment, and that bending moment results in the development of rotation at the full member level. Rotation is the flexural deformation at the full member level, and it can be defined as, for example, if you have a column which is, let's say, undeformed, and after the application of bending moment it deformed in a certain manner, the rotation of the angle between the original undeformed configuration and the deformed configuration at the end is called end rotation. It is represented here as theta. Similarly, you will also have an end rotation here, theta. So this bending moment will cause flexural deformation, which can be measured in terms of the end rotation, which is theta. So the relationship between m and theta in a linear elastic model is always always linear. So if you plot, for example, how much bending moment is applied and how much rotation is produced in a linear elastic model, this relationship will remain linear straight line forever. You can apply an indefinite amount of very high amount of moment and you will still get a very high theta, regardless of whether the actual column will be able to uh, handle that high bending moment or will be able to uh, develop that particular bending moment and corresponding theta in it or not. Maybe the actual column will fail far before the development of that particular bending moment and the corresponding theta. In that case, your linear elastic analysis will be completely wrong, because it will not be able to predict or capture the failure of your column, and it will give you a kind of wrong answer, or it can deceive your design decision making. So therefore, if you want to capture the actual behavior of your structure or your elements, you should always consider nonlinear modeling. And obviously, for the performance based seismic design, nonlinear modeling and nonlinear analysis is at the core of it, because it tries to capture the actual behavior of the structure instead of just following a particular building code and following the implicit provisions. So in performance based design, we start with an initial design, and then we check explicitly using nonlinear modeling and nonlinear analysis that this particular design uh, is fulfilling the performance requirements and the acceptance criteria which we set at the start of the design process. So therefore it is very important to develop this particular skill of nonlinear modeling in practical design practice for reinforced concrete buildings, especially for those kinds of structures for which the prescriptive provisions are not available, or the current provisions maybe are not applicable to such kind of structures. For example, new structural systems, or structural system with innovative materials or innovative shapes, innovative geometries and all that. So let me just go back one more step and explain the same concept uh, in using the example of a reinforced concrete beam. So for example, if we have uh, a particular frame, a portal frame for example, two columns and a beam, and let's assume that it is made of reinforced concrete, and then it is subjected to lateral force, let's say this lateral force P. Now we know, and we will discuss only about the beam for example in this case. We know that the maximum bending moments will be at the ends of these two beams, and and that bending moment will be produced by this applied action, applied force P, and it will experience the maximum bending moment at both ends, and as expected that the maximum inelastic action also should be experienced at both ends of that beam. Now in case of a linear model, in case of a linear model of this beam, the relationship between that m, which will be uh, which will be applied action at this particular beam, and the corresponding theta. Let's say this beam deflects like this, and obviously the end rotation will be this angle. If I take a tangent of deflected shape at one corner, one end, the angle which it makes the the original horizontal axis will be theta, and similarly there will be a theta on the other end also. So in a linear model of this beam, the relationship between m and theta, as I have said, is always linear forever. Same example can be given for a column also, and for any frame element it will be forever linear. If you apply some unrealistically high p, the model will predict an unrealistically high theta and corresponding deformations and all the other results. Uh, Regardless of whether that unrealistically high p, that bending moment produced by that p will be able to the beam will be able to develop that or not, or will fail or not. In a nonlinear model of the same beam, we will actually try to make this behavior as realistic as possible or close to a real behavior, and that real behavior is that up till a certain moment the relationship between the m and theta will remain linear, but after a certain moment when a particular value will cross, which corresponds to the capacity of that moment capacity of that beam, the relationship will no longer remain linear, and then there will be high values of theta even without any significant increase in bending moment. So there is a limit on bending moment which the particular beam will be able to develop in itself, and that will be the moment capacity of your beam. And once it is reached, then it will no longer increase bending moment, but only theta will increase. And ultimately when theta will also exceed from the deformation capacity of your beam, then it will fail like this. So this level of moment is the moment capacity, I can say moment capacity, and the last useful theta after which the beam will significantly damage or significantly fail, that can be called as that like theta capacity or the rotation capacity of the beam. So there is a moment capacity, a maximum moment which the beam can develop, and there is a rotation capacity, the maximum rotation which the beam can safely develop, after which it will just fail, right? So we kind of replace this linear moment rotation behavior with this non-linear moment rotation behavior in our computer model, and this is the difference between a linear model and non-linear model. Now if the beam is behaving like this in the second model, and if I apply some force which exceeds the moment capacity of the beam, in that case the model will be able to predict that failure. Model will be able to show after the analysis that this beam have yielded significantly, right? Now when we define this moment versus rotation behavior directly at the member level in our computer model, this is called the plastic hinge modeling approach for reinforced concrete beams or columns. But there are other approaches also to have the effect of nonlinearity or include its effect. For example, in fiber modeling approach, we directly incorporate the nonlinearity at material level and not at the member level. But here what we are doing, we are directly making the moment and rotation behavior as nonlinear. So I can just write it somewhere here that in fiber modeling approach, we directly make the sigma versus strain, the stress strain behavior of material, we make it nonlinear. We replace it with the elastic modulus which we have provided in the linear model. We replace it with the actual stress strain curve, the complete curve which is nonlinear. But in plastic hinge modeling approach, which is currently being discussed here, we directly incorporate the nonlinearity at the member level. Member level means that whatever is the member action, which is moment, and whatever is the member deformation, which is the rotation in this case, we directly make a incorporate a nonlinear behavior at the member level directly. So we directly tell the program that this member itself is a nonlinear member. And the practical way to do this or telling this to program is by defining what we call as plastic hinges. So in nonlinear model, we define and incorporate in our computer model what we call as plastic hinges. Define plastic hinges. So plastic hinge is a way to tell the program that this particular element will be following this moment versus rotation behavior, which is given by the user itself, instead of just following a linear relation forever, right? So how we define plastic hinge? That it is you can say a hypothetical element or a hypothetical spring, you can say. So it is uh, a hypothetical element. Actually it is a zero length element. Zero length element means that it is just a point which you can assign along the length of your beam anywhere. At this particular example, when the beam is subjected to lateral load, since the maximum bending moment is experienced at the ends and therefore the inelastic action is expected at the ends, therefore you can provide these plastic hinges at the ends only, and in between the two ends you can assume an elastic or linear element, linear frame element. So since you are assuming that the inelastic action is only concentrated at a certain point where the plastic hinge is provided in the model, therefore this approach is called the lumped plasticity approach or concentrated plasticity approach. So currently we know that plastic hinges are zero length elements, or you can say some points along the length of your element which you can define or provide, and those points or those zero length elements have just one basic input and all other inputs are associated with that, and that basic input is the nonlinear moment versus rotation behavior. So you are forcing your program when you are defining a plastic hinge, you are actually providing this moment versus rotation behavior to your program. You are forcing that at this particular point the program should follow this given moment versus rotation behavior instead of just following the linear relation forever. So when I define a beam with the elastic frame element and then I incorporate 2 points at both of its ends, these 2 points are the plastic hinge elements, hinge 1 for example and then hinge 2. The basic input for both of these hinges will be a moment versus relationship m versus theta curve, which I will define as an input for this particular hinge, m versus theta at both ends, right? And in that hinge I will tell the program that okay, this is the moment which is the yield moment of this beam. This is the rotation which is the maximum rotation capacity of the beam, beyond which the beam should just fail and the the moment should reduce and it should be just reduced to just a fraction of the yield moment, for example the residual moment. So all the inelastic behavior is captured in that curve, and that curve we have to give as an input in the program to tell it that this is the inelastic action lumped at these two ends only. In between you can use an elastic frame element just like the linear model, but you incorporate at the ends two additional components or two additional elements, you can say hypothetical elements, zero length hinges, and those hinges have this basic input m versus theta relationship. Now there will be several other inputs also, but those will be just related to that. For example, how this m theta curve should unload and then reload if there are if the loading is not in one direction, if the loading is in both directions and it have different cycles of loading and unloading, we have to define how it should unload, reload and all that. But basic thing is the relationship between moment versus theta. Now if we define this kind of a particular plastic hinge, we are only making moment behavior as nonlinear. We are not making shear behavior as nonlinear, right? So we know that there are actually 6 actions in a three-dimensional frame element. So if we have, for example, this frame element in 3 dimensions, there are 6 actions associated at for with this 6 actions. We know that those 6 actions are the axial load. Let's say, let's say n axial load, axial action. Then we have 2 bending moments. Let's call them, let's say, m1, m2, and then 2 shear forces. Let's say v1, v2, and then there is a torsional moment also, the moment about the vertical axis. So there are 6 degrees of freedom at each end of a frame element, three-dimensional frame element, and each of these degrees of freedom have a corresponding action and a corresponding deformation also, right? So uh, all of those 6 actions have a deformation, and the relationship between those actions versus deformations is by default linear forever in a linear computer model. So 6 actions versus 6 deformations, all these relationships between them will be linear for linear model, but we can make each of them as non-linear also using the idea of plastic hinges in non-linear modeling. But currently, out of those 6 actions, this particular example which I just showed you on the right hand side of this figure, that is only making one particular action, which is the moment about one axis, one particular axis, versus the rotation of that moment. I just made it non-linear only for one out of those 6 actions. But using this plastic hinges, you can have any of those 6 actions, you can make them non-linear, the relationship between actions and deformations. For example, for a column, if you have, let's say these are the two nodes of your column and it is subjected to axial load P, for example, and you want the relationship between axial force and axial shortening as nonlinear, then you can use a particular plastic hinge to do that, and that will be axial hinge now, not the moment hinge. So the particular plastic hinge which I used to demonstrate the example of a beam is actually moment type hinge, which takes the moment versus rotation behavior as an input. But if you define an axial type hinge for this particular column example at the bottom right, in that case you will be defining axial force versus axial shortening behavior as nonlinear if you want to do this. Similarly, in a beam also, if you want the shear behavior to model as inelastic, you can use what we call as a shear hinge or a plastic hinge of shear type. In that case, the input required for that particular hinge will be shear force versus shear deformation nonlinear behavior, just like moment versus rotation nonlinear behavior. So I can summarize this whole discussion maybe here, that you have 6 actions versus deformations for a frame element, three-dimensional frame element. 6 action versus deformation uh, relationships, and let me just count them again also for you. Let's say that this is your beam or any, let's say, frame element, it is going in that particular direction. uh, so there will be two cross-sectional axes, let's call them 2 axis and 3 axis, and 1 axis by default is the longitudinal axis. If I talk about the ETABS or SAP 2000's local axis orientation, so then 2 and 3 axes are actually the cross-sectional axis and 1 is the longitudinal axis. So 6 actions corresponding to these 3 axes will be, the notation would be, let's call that uh, P as the axial force, and it is actually, P can be also represented as, for example, the force in the force along axis 1. Then the second action will be, for example, V2, which is the shear force along the axis 2, shear force along axis 2. And then V3 is the third action, which is the shear force along axis 3. Then you will have moment M2, which is the moment about axis 2, moment about 2, and then M3 will be moment about axis 3. If this beam is subjected to, for example, gravity load like this, then the primary bending moment will be M3 caused by that gravity load, and the primary shear force will be, major shear force will be V2 for that gravity load. And last thing is the torsion. You can say it is the moment about axis 1, moment about the longitudinal axis. So forces, three forces and three moments. These are the total 6 actions which your frame element may be subjected to. Each of these actions have a deformation associated with that. For example, axial load have a deformation which is the axial shortening or axial elongation, which is represented here by delta. Similarly, shear force in both directions will have shear deformation. Let's say represent them using gamma shear deformation. Similarly, V3 will have gamma 3. In that particular direction, you can have shear deformation. M2 will have theta 2, which is the rotation about axis 2. M3 can have a deformation which is theta 3. And similarly, torsion will have a twist. Let's represent that twist with let's say some other symbol, maybe phi, for example. So let me just write twist here so that you do not mix it with any other notation. Sometimes in different textbooks the curvature is also represented by this symbol phi, but we are calling it as twist or twist angle. How much the cross section is rotated along the axis 1, about the axis 1. So this is the rotation about axis 2, rotation about axis 3, and rotation about axis 1. So each of these 6 relationships, P versus delta, V2 versus gamma 2, V3 versus gamma 3, and so on, each of these 6 relationships is linear forever in a linear elastic computer model, and you can just simply define some constants which will become the slope of these relationships. For example, when you say that your material have a elastic Young's modulus which is constant forever, defined by E, and then when you say that your cross section shape has a particular width and depth, the program can calculate the second moment of area or moment of inertia. So EI will become the flexural stiffness, which can be combined with the length of the element to make a constant slope for the moment versus rotation behavior, and that will remain constant forever. But the point is, for nonlinear modeling, you should keep in mind that any of these 6 relationships, you can make them nonlinear. You can force the program to follow a nonlinear behavior between any of these 6 relationships, 6 actions versus deformations, by using the idea of plastic hinges. So plastic hinges also can be of these 6 types. Actually, you can say 3 types or 4 types, because these two are the shear forces, is just a matter of the axis. Similarly, this is the axial, and then these two are the moments, and then torsion. So you can have flexural plastic hinges or moment plastic hinges. You can have shear plastic hinges, which will take the relationship between V and gamma from U as an input and use that in your model. And then you can also have for example, axial plastic hinges, and torsion plastic hinges also you can have. so which will take the relationship between torque and twist as a nonlinear behavior from the user and define it in the program. So you can have plastic hinges of several types, and you should know that what behavior you have to provide while defining that hinge. So this particular example, again I will go back here, that when I use the moment versus rotation example to explain the basic idea, I was using actually a moment plastic hinge, and if my major applied load was gravity load, then the primary bending moment will be m3 and theta 3. So I will be using that behavior was actually this one at the bottom, which I was making as nonlinear, but you can make any of these behavior nonlinear. So I will show you in SAP 2000 demonstration that you can select any of these hinge types, and then the corresponding action versus deformation behavior you have to provide. So this is the basic idea of what a plastic hinge is. So let me now quickly go through these slides. They show exactly the same idea. For example, for columns here, that the relationship between moment versus theta. So this is moment on y-axis and theta on x-axis. This blue line you should provide to the program, and when you provide it to the program and apply the cycles of loading and unloading, the program follows a behavior or predicts a behavior which matches very well with the experimental results. So your computer model will behave like how your actual column behaved in a real experiment. So now you how to get this moment versus rotation behavior, this itself is very important obviously, and it's the natural next question once we are familiar with the idea of plastic hinges, that how to get this behavior in order to give it as an input in the computer program. How we get this blue line for each column and for each beam in our computer model. And obviously one direct answer to that question would be that this can be obtained using experiment. You actually subject your beam and column to the loading such that it produce bending moments in that, and then see or actually measure how much theta was produced for each bending moment. But obviously you cannot do it for all types of columns, beams which you have in your computer model. So in that particular case you have to rely on different modeling guidelines, and one of the very important guidelines which not only provides the modeling parameters but also a detailed procedure for performance assessment of new and existing buildings. That guideline is ASCE 41. So one easy approach is to follow ASC 41 and get the modeling parameters, which means the actual moment versus rotation behavior or any action versus deformation behavior which you want to make nonlinear in computer program. So you get those parameters or behaviors from this ASC 41. So how this works is that ASC 41 describes or explains first a general force versus deformation behavior. So this is on y-axis is a action, any action, it can be moment, shear, axial load also, depending upon what element you are modeling as nonlinear, and on x-axis is the deformation, right? So it defines a general template for any action versus any deformation. The first point is the yield point, then is the ultimate point, then the point D where the action was dropped, or actually the capacity was dropped to a certain residual value, very small value, and then finally the last point beyond which the element is completely failed or completely gone. So these points it define, and then it gives you the shape of this actually the values of all of these black line in the form of three modeling parameters, which is called small a, small b, and small c. Small a is actually the deformation value from yield point up till the ultimate point, and small b is the starting from yield point up till the last point on that action versus deformation curve. So for example, if I want to model a reinforced concrete beam using the moment hinge, this ASE 41 will give me that how much rotation will be there in my beam from B to C and then from B to the last point, based on what reinforcement I have, what cross section size, what FC prime, what Fy for example. So based on the material properties, the cross section size, and the amount of reinforcement and everything, in detailed table from ASC 41, I can pick my A and B and C value. C is actually how much is the residual strength left once the ultimate point is crossed already. So this is corresponding to the strength loss. So before this point B, this linear line, the program already have all the constants to actually define this slope, because the linear properties the program already have. All we need to define is the behavior beyond the yield point, right? So therefore a plastic hinge element in SAP 2000 or ETABS is actually a rigid plastic hinge. The moment versus rotation behavior before yield point of a particular beam, you don't need to give that behavior. You can start your plastic hinge directly from the yield point my onwards like this. So the linear part of the curve you don't need to define in the program already have it. So it will follow that linear line before the moment cross this my value which you will give. Once this my value is crossed, or the capacity of the beam, the B point is crossed, then the plastic hinge will start having its role in the analysis. Before that, the plastic hinge will not have any role in the properties of the structure. So once the bending moment cross from the capacity, it increase from the capacity, then the hinge will be activated during the analysis, and then it will tell the program that now the bending moment should not increase indefinitely with the applied loading. It should increase up till a certain level, maybe with this slope, and then beyond that it should just come down and the beam should be considered failed. So this is called rigid plastic hinge. Rigid plastic hinge means that the linear part of the behavior there is no need to define, and it can be just behave in a rigid manner. Rigid manner means that in the linear range of response of that beam, it will simply act as a rigid component. It will not incorporate any of the stiffness in the model, and the model will simply follow a linear default behavior. But once the moment increase from the yield point, suddenly it will activate, and then it will follow, instead of linear slope, it will follow the plastic behavior, or whatever is the post yield stiffness we give, it will follow that one. The shape is still in our hand when we define that hinge in the program, but I was telling you that ASC 41 follows it prescribes actually a standard shape of any action versus deformation, and then it provides the required constants to plot that shape. So this my will be actually the function of three things: the cross section of that beam, the amount of reinforcement, and the material properties. So all of these three things actually will make this my, and once this my is crossed or increased, the applied loading is increased from this number during the analysis, the hinge will activate, and so it will behave like a rigid element before yield, and then it will behave like a plastic element after yield. So therefore all the hinges in SAP 2000 and ETABS, they are like rigid plastic hinges, which mean you don't need to define the initial straight line from A to B. You can just start them from B onwards, because from A to B the program already have that behavior with it, so we don't need to define it. So we therefore ASC 41 started directly and focused on the plastic rotation. So A and B are the plastic rotations. Plastic rotation means that it doesn't include the elastic part of the rotation on x-axis. So they start from theta y onwards. So therefore they are plastic rotations, and A is the plastic rotation up till the ultimate point, B is up till the last point on the curve. Now C is the residual strength. It is the proportion of how much uh, strength from original value it remain. For example, if we say its value, if ASC 41 says that its value is 0.1, which means that C will be simply the residual moment will be simply 10% of the ultimate moment. So this number will be actually this particular height. On y-axis, the value is already normalized by the yield quantity of that particular action. For example, if I am plotting moment versus rotation, then it is already m versus my, and my we can manually calculate also. It is a function of three things I have said already: cross section, cross sectional stiffness, for example the uh, width and depth, and second thing is the amount of reinforcement, and third thing is the material properties, Fy, Fc prime, and elastic modulus and all that. So these three things we already have it, so we can just normalize the y-axis with the capacity. So the B point is actually corresponding to a value of 1, and from that onwards the actual inelastic action starts. Now A, B and C are called the modeling parameters in ASC 41, and for any action versus deformation you can have detailed tables based on your properties of your element. You can pick these A, B and C values, and then you will be able to plot it and put it as an input in your computer program as the properties of your plastic hinge. The second thing which ASC 41 also provides is called as the acceptance criteria or the capacities, and it provides three numbers actually, each corresponding to a particular performance level, and there are three standard performance levels we generally use in the performance based design of beams of basically reinforced concrete buildings. One is called the immediate occupancy, then life safety and collapse prevention. So the deformation corresponding to each of these performance level is actually is called the acceptance criteria, or your capacity is corresponding to those performance levels. So these are the three rotation values. This one, for example, called theta IO. This is, let's say, theta LS, and then last one would be somewhere here, let's say theta CP. These three numbers will also be provided along with A, B and C from ASC 41, and then you can put these markers on your input moment versus rotation behavior for beams, and the program at the end of the analysis will tell you that whether this beam have crossed IO or crossed LS or crossed CP or not. So you can check the performance of this beam after the analysis in terms of these three performance levels, if you provide the corresponding capacities or corresponding acceptance criteria in terms of deformation. So these three numbers, I will repeat again, won't have any uh, uh, won't have any effect on your analysis. They are just markers on your uh, actual given input to tell the program that these are the points corresponding to my performance levels, and after the analysis I will be checking whether these performance levels were exceeded during the analysis or exceeded by the applied loading or not. So they will be just to check the performance at the end of analysis. They won't have any role in the analysis. They won't modify anything in the analysis results. So two things we just covered now: modeling parameters in ASC 41 and the acceptance criteria. These are actually three numbers. In this particular example case of beam, they will be theta IO, theta LS and theta CP, and you will see that theta IO will correspond to very low levels of nonlinearity like just yield point. Theta ls will be somewhere the moderate level of nonlinearity. Theta cp will be close to complete collapse or complete failure of the beam. So these 6 numbers you can pick from ASE 41, A, B and C modeling parameters, and the 3 rotations corresponding to each performance level. So this is the most widely used nonlinear modeling approach for reinforced concrete beams that use ASE 41. So ASE 41 also have some, it also gives you some control on the shape also, but we'll just skip that one, that whole discussion. So in in terms of hinge properties, let's see now the actual table from ASE 41, which actually gives you these 3 uh, modeling parameters and 3 acceptance criteria. So here this is the ASCE 41 table for modeling of reinforced concrete beams, and it is table 10-7. It is actually 41-17. Now you can see here that based on your conditions, all of these things here, ultimately you can select a particular row which is applicable to your reinforced concrete beam, and then you can pick, for example, for one particular row you can pick 6 numbers. One is A, B and C, and then the plastic rotation angle corresponding to IO, LS and CP. So once you have these 6 numbers, you can define your moment versus rotation behavior, and obviously it will be now a rigid plastic behavior. So it directly start from yield point, go to ultimate point, and then come down and then just finish at the end, maybe some residual value, and then go down. So you already know what is A, this how much is the rotation corresponding to A for your beam, how much is B. So you know all these x-axis values, distances, and then you also know this yield point. This is corresponds to my. You can calculate it manually. The program also can calculate it for you. How much is this height? That is small c, actually 20% of the value of your moment capacity, and then 3 markers on it. So you can see that these 3 will be somewhere here like this: theta, IO, LS and CP. So this table will enable you to actually plot that moment versus rotation behavior and also the acceptance criteria on it. Similar table you can find for reinforced concrete columns or for any other elements also. So similar table you can find in ASE 41 for columns also, but obviously for columns it will be uh, a bit complex because the axial force also interacts with moment in case of columns. For beams, the moment is considered uncoupled from the axial action, but for columns obviously they interact, and therefore you have to take that interaction in account. So this figure tells you how much the actual rotation looks like. For example, a 0.01 degree rotation is, for example, on the figure on top left you can see that a rotation of 0.01 will not cause any significant damage. On the top right you can see it is 0.02, this one, and then 0.05 you can see here some cracks, and then this is 0.06 radians. 0.06 radians you can see have significant damage at the ends. So using these figures you can roughly understand how much are these rotations. For example, you can see that it is 0.01 is the collapse prevention for this particular case. So you can imagine how much damage this would look like: 0.05, 0.03. So you can make a picture in your mind about these rotations. Just a quick overview of what inputs are required to just use that table. You require the information about your reinforcement, row value, and row prime is the top and bottom reinforcements. You need the information about transverse reinforcement. This is longitudinal steel, this is transverse steel, whether it is conforming or non-conforming, and at the bottom it mentions what how to check whether the transverse reinforcement is conforming or not. And then this parameter, which is a function of shear force in the beam, function of the cross sectional geometry B and D, function of the FC prime, expected FC prime strength, which will be higher than nominal value, and this factor, depending upon that, you can pick the uh, plastic rotation and acceptance criteria. So maybe because of shortage of time, I may not be able to go into detail of actual calculations, but I can give you an overview of what the procedure is, and then later on in another session we can discuss the calculations also for real case. Another thing you should keep in mind is that all of those first set of inputs are for beams which are controlled by flexure. But there can be beams which are controlled by shear, and then by inadequate development or splicing, and finally by inadequate embedment into beam column joint. So if you are having, for example, a condition 4, in that case no need of other input required, you can directly use the last column. But if you have a beam controlled by flexure, then you can go into the details of these three parameters. So one, this parameter about longitudinal steel, second parameter is about transverse steel, and third is a combined factor uh, which you can see and again get its value and then decide about which row is to be selected. And it recommends, I think, interpolation between different rows using linear interpolation. You can pick the values if more than one row is applicable for your particular beam. Most of the cases this will be the case because you have three input parameters, and many times two rows are applicable and your values are in between two rows, so you can interpolate in between them. So this was an overview of plastic hinge, uh, plastic hinge approach, uh, and I think now I can go to the SAP 2000, and then can actually show you the process of defining a plastic hinge, and then how we can give some inputs and all that. Now I will open a SAP 2000 model